Right, so let me show you how to set up the program and run it. These are the files that I have given you in the compressed tar archive, and I provide also a mini set of malware samples, behavior profiles from ClusTheDroid. Before you can compile it, you need to get the JSMN library, which you can get here. This is the URL. And just download the repository and compile the library. After you've done that, you need to you need to edit the make file so as to point. After compiling the JSMN library, you will get a static library, leap JSMN.a, and you need to set in the make file the JSMN variable here. So set the path to the static library you get from compiling the JSMN library. After you have done that, you can basically install the application like that, and we will just run the. After that, you will get after compiling the application, you will get a file called ClusTheDroid, which you simply run. The de-identifier specifies the directory. Right now, we want to cluster these samples in the mini folder. You can see inside the mini folders there are two specific folders, each with ADRD malware and one folder with PJAPS malware. So we do the clustering. We specify the directory of where our sample behavior profiles are, and then we just let it run. You can see we use single linkage in this clustering. Right now it's parsing the behavior profiles, and now it's done. What you can see is that there were 51 files entirely. Out of these 51 behavior profiles, 40 of them had more than one feature. One or more, that is more than 0 features. And 11 files did not have any features, so they are not used in the clustering. This shows the effectively samples that we clustered. So we have 30 behavior profiles belonging to PJAPS and 10 behavior profiles with the ADRD label, and that gives us a set of 40 feature sets all in all. Here you can see a result from the actual clustering. You can see this column indicates all the merges. All in all, we had 39 merges, which so we cluster it entirely. We create the entire dendrogram. That is after 39 merges, we will have one cluster when we are clustering 40 samples. You can see the similarity threshold, that is the combination similarity for each merge, the precision recall C index, and the number of active clusters. So here you can see that right around here we have near optimal clusters. We have a precision of 95, a recall of 72.5, and you can see right before that the C index actually makes a huge jump compared to the previous increases of size in the C index. We can do some more. We can specify if we would like to see the clusters here, see the specific division of samples in the clusters. We can run our clustering algorithm with the identifier K and say which is the merge of which we want to see the actual clusters, and in this case it's 34. So we run it again, and again we use single link. And here you can see after the merge 34 we print out the clusters. All in all we have 6 clusters as indicated here, and these two are the ones where ADRD samples are in. There are 2 false positives in the sense of PJAPS, and all the rest of the PJAPS is just in their own cluster. And it's easy to see that the precision decreases from 95 to 77.5 in one merge. So obviously this cluster merges together with one of the PJAPS clusters in the next, that is in the 35th merge. We can also use another linkage criteria other than single link. You can, for example, use complete, and we can also specify single, which is default. Let's try to do it with complete linkage and see what the differences is in the accuracy of our clustering scheme. You can see that it looks a bit different than what we previously had. All in all, I think single link shows a better precision again. I think here's near optimal clusters or so. And it's funny, you can see that there's a huge, again, a sudden increase in the C index value right around the near optimal clusters. The last thing I would like to show is you can also compile it with some debugging information, and this basically gives you the ability to see how the clustering was evolved. You specify the directory again, and then we run it again. We have single link. We don't print any of the clusters at a point, but after the clustering, in this case, we will have we will print out the entire dendrogram of our clustering process, cluster run. So right now you can see we have also we have all the entire dendrogram. It's a binary tree. We show it in a primitive manner, in a naive way. And you can see this is the path. This is a sample. These are two samples that are clustered, merged together into one cluster, and you can see the path to the samples. So this is this star 6, 7 starting characters of the MD5 sum of the sample. And you can see the numbers here indicate which merge are happening here. That is this cluster merging with this cluster. So this is the first merge we have, this is the second, this is the third. So you can see this is the big ADRD family that we showed also when we printed out our clusters, and we have a large PJAPS family here. Here you can see two large PJAPS family merging together and merging at the 35th merge. They combine into, they cluster together with the ADRD family, hence why our precision decreases a lot, because all the ADRDs are clustered together with the PJAPS. Yeah, I think that's about it. Super duper.